All right, how's it going? Welcome back to another video here in the series on differential equations. It has admittedly been a little while now since I have made a video here on this video series. And first, I apologize for that. Life has kind of just been getting in the way for one reason or another, and it's caused me to be making videos less frequently. That being said, though, that I have no intention on stopping the process of making videos. I still very much enjoy doing it, it's a lot of fun for me. So I'm going to keep continuing making these videos, but I do just want to give a bit of a heads up that I'm going to be making videos when I can. The ideal goal is 2 videos per week, but now it's starting to look more like 1 video per week. But we'll see, right? I'm going to do what I can to keep making videos consistently. So that being said, I want to kind of just quickly recap what we were doing in the last video and show how going from differential equations in the last video to differential equations in this current video, what changes and what kind of generalizes. And then just to talk a little bit about what those generalizations mean before really diving into everything. Okay, it's a lot of words without a lot of meaning behind them. So let's actually explain what I'm talking about, right? So in the last video, we were looking at non-homogeneous differential equations, which means essentially that we have a non-zero right-hand side. And what was new and unique about the last video is that no longer do we have a constant times the first derivative plus another constant times the function y itself, equaling some right-hand side. But now we all of a sudden said, well, let's see what happens when this constant all of a sudden becomes a function of x. So we have a of x, and let's see what happens when this becomes b of x, right? So how do we solve these types of differential equations? That was the focus of the last video. But still, with this structure for a differential equation, this is still inherently a linear differential equation. And every linear equation pretty much that we've been working with up until this point has been a linear differential equation. But you might be able to tell by the title of the video that we are now going to start to go into the non-linear regime. All right, start to say what happens if we no longer have a non-linear differential equation. So first thing that I want to do again is just to point out what changes going from here to the non-linear case. So what I'm going to do is I'm going to write out nonlinear. And in order to talk about a nonlinear differential equation, I think it really makes sense to first make sure we understand why this is in fact a linear differential equation. So this differential equation that I already have written out is linear because we have something times the first derivative plus something times the function itself equaling the right-hand side. And when I'm saying something times the first derivative, I want to emphasize that it's something times just the first derivative by itself, rather than the first derivative squared, the first derivative raised to the 12th power, or the sine of the first derivative, or anything along those lines. We purely have just the first derivative. So the fact that we have just one single power of that, plus something times just one single power of y of x, rather than y squared, y cubed, square root of y, whatever it is. The fact that we have that structure in the dy dx term and the y of x term is what inherently makes the equation linear. So naturally we can say, well, how is this going to generalize when we look at nonlinear differential equations? And the case where we have nonlinear differential equations, I guess quickly put, is that now we no longer need to have just linear powers or linear powers of the first derivative and not just linear powers of the function y itself. We can have various powers or other types of functions. So what I'm going to do here is I'm going to start with this equation, and I'm now going to subtract f of x over to the left-hand side, and then I'm going to kind of encapsulate f of x in this term right here. So when I do that, let me actually erase nonlinear for now. So when I do that, I'm still going to have a of x dy dx plus, and now I'm going to put maybe in brackets, b of x y of x minus f of x equals 0. Okay. So what I'm doing is right now subtracting this f of x over to the other side. So this term right here, in the general case, when we have a non-linear differential equation, is this doesn't need to be some function of x times just y to the first power minus f of x. But again, if we're allowing ourselves to have either higher powers of y or just sine of y, cosine of y, e to the y, or anything along those lines, the idea is that this term in brackets no longer needs to have this structure, but we can say in the general case that this term in brackets is some function that depends both on x and it depends on y, where the function does not need to just have y to the first power right here. So what I can do is rather than write this thing in brackets, in the general nonlinear case, I can just say that this thing right here is equal to some function, is that the notation? Yeah, we'll go with this. Some function of both x and y. All right. Now, you might be wondering, why not also have this be a function of y prime? And that would be a perfectly valid question to ask. And I would say just hang with me for a second here. And I'll answer that part in a second if that's what you're wondering. Now, for this term right here, again, we could say that rather than just having one power of the derivative, we could have the derivative squared, derivative cubed, or whatever. And what we're going to do though is we're actually, for the purposes of this video series, is we're going to leave this term alone and say that in generalizing from this equation to the nonlinear equation, rather than just having a of x, we're going to have a of x comma y. So this coefficient can now be a function of both x and y. So let's see. So this thing, maybe rather than calling it a of x, maybe we call it p of xy. So then going from here to here, the generalizations that we're going to make with the non-linear case is this. Non-linear differential equations, for the purpose of this video series, can be written as p of xy dy dx, right? And then plus q of xy equals 0. Now, there are two reasons why I wanted to kind of spend a little bit of time going from here down to here. The first thing is, if I were to just show this equation immediately, we might say, well, isn't that just a homogeneous differential equation because we have 0 on the right-hand side? And I really wanted to show that it doesn't need to be homogeneous. You could start with a non-homogeneous term and just encapsulate this f of x right-hand side into the term in brackets, which is this q of xy function right here. So even in the general case, this could represent a non-homogeneous differential equation. Okay, so that's the first reason why I wanted to do that. Second reason, and kind of the question that I already mentioned, is why are we saying that these coefficients only depend on x and y rather than x, y, and y prime? And then also, how come dy dx isn't raised to some other power or sine of y prime or e to the y prime or anything like that? And the answer to that is, first, well, you could. In theory, you could have a nonlinear differential equation where these functions p and q depend on x, y, and y prime. And this dy dx term can be, doesn't just need to be raised to the first power. The reason why we are saying that nonlinear differential equations are going to have this form really just has to do with an issue of convenience. It turns out that the field of nonlinear differential equations and attempting to come up with solutions for nonlinear differential equations is this massive area of math. And there's no realistic way we could cover all attempts to solve nonlinear differential equations. just in this video series. It's just not realistic. In fact, it turns out that many different nonlinear differential equations don't even have analytic closed form solutions. So what we're going to say then for this video series is that when we are talking about nonlinear differential equations, these are the generalizations that we're going to make, but we're still going to assume some loose structure where we have some function of x comma y times just the derivative to the first power plus some other function of x and y. And obviously we could generalize more, but to keep it relatively simple, this is a first video series on differential equations. We're going to say that even the nonlinear ones are still going to have this structure right here. Okay, so hopefully that makes sense. Again, we're not saying all nonlinear differential equations have this form, but rather the ones that we're going to be working with have this form. All right. Now, I wanted to also say that because that kind of leads into what we're really going to be talking about in this video. Because what we've been doing the past couple of videos is to say, well, how do we solve these different types of differential equations when maybe they are non-homogeneous, or maybe when the constants are no longer, or rather when a and b are no longer just constants, but rather functions of x, right? The goal was to say, how do we actually solve these types of things? And we're going to be doing the same thing here. We're going to be saying, how do we actually solve these types of differential equations? So what I want to mention is that, again, many nonlinear differential equations just simply don't have these analytic closed form, nice, pretty looking solutions that you could write out on a whiteboard. So what we're going to be doing is we're going to say, let's look at a couple types of nonlinear differential equations, a couple types of equations that have this form right here, and the couple types that we're going to look at are kind of these special cases of nonlinear differential equations which do happen to have these analytic closed form nice looking solutions. So we're going to kind of pick out a couple of special cases, a couple of special cases for equations that have this structure right here. So by no means is this video going to be exhaustive of all nonlinear differential equations. It's just can't do it, right? The video would be significantly longer than however long this video ends up being. So hopefully all that makes sense, and I wanted to say that so we don't get our hopes up saying that this video is going to be the one-stop shop for solving all nonlinear differential equations. All right. So what I'm going to do next is I'm going to erase the board. We're going to cover two special types of nonlinear differential equations. The first one is called a separable nonlinear differential equation. So I'm going to write out what it means for a nonlinear differential equation to be separable up here, and then we're going to go through that together. Okay, so the first type of nonlinear differential equation that we're going to look at is called a separable equation. So let's go through the definition together. It says here that a first order differential equation is considered separable if it can be manipulated into the following form that we have right here, where we have some function of y, q of y, times the differential dy, equaling some other function p, which is a function of x, times the differential dx. And of course the idea here is to solve this differential equation so that the solution is going to be of the form y of x equals something. Okay. And I wanted to start with this one, because it's probably the easiest type of method that can be used to solve a nonlinear differential equation, but also because this is actually something that we've seen before, where maybe I'll just write out an example right here to show that we've already done something, and this is just kind of the general form of something that we've already done. It's the whole separation of variables technique. So if we have a differential equation that starts out as maybe dy dx equals, I don't know, minus 3y or something like that. what we have done is we could say that if we were familiar with linear algebra, we can recognize that the exponential function is an eigenfunction of the derivative operator. But we also said that if we weren't so familiar with linear algebra, that was okay. And we could kind of solve this differential equation through separation of variables. And we'd say, okay, well, what's the process for doing that, right? Well, we just divided y to the other side, so we had dy over y. And then we multiplied dx over to the right-hand side, so we had minus 3 dx. And then we went about integrating both sides, so that we ultimately were able to solve for y of x. And that process that we've gone through is really just the same process that is being outlined right here. In this specific differential equation, we would say that our q of y function, so maybe we could just write this, that q of y, in this case looks like it would be 1 over y. 1 over y, right? So then we have 1 over y times dy, in other words, q of y times dy. And then our p of x function, in this case, just happens to not depend on x, but that doesn't mean that it can't, in the general case, be a function of x. In this case, p of x just happens to be the constant negative 3, right? So when you have negative 3 times dx, then that's the same thing as p of x times dx. All right, so this is actually something that we've already done before, but now we're just trying to really highlight that this is the general form of a nonlinear differential equation which is separable. So because kind of when we were talking about applying this separation of variables technique to differential equations, we started out by just saying this is for very simple differential equations to solve, right? What we're going to do next is I'll keep this up here on the board, but we'll show that there's a much, I guess, uglier, if you want to call it that, but much more detailed or non-trivial type of differential equation that happens to be separable, and we're going to show how to solve that type of differential equation with separation of variables. All right, so now we have this very much, I guess, non-trivial looking nonlinear differential equation, and we're going to show how first this is a separable differential equation, and then we're going to show how we can apply that technique of separation of variables to actually solving it. Okay, so here's the example. It's this quantity x squared y minus 3y times the first derivative minus 2xy squared equals 4x. Okay, so usually the first thing to do I guess kind of the straightforward step when checking if a nonlinear differential equation is separable is you want to get the derivative term by itself. And this again is part of why we're going to say that for the purpose of this video series, that nonlinear differential equations are still going to be some function of x comma y times just the first derivative. Because when we have plus some other function of x and y. Because when we have differential equations of that form, it's very easy to isolate for that first derivative. Okay, so let's go about doing that. If we're going to isolate for the first derivative, we're going to get dy over dx equals something. So let's start by writing that out. dy dx equals something. And to isolate for it, right, we need to just add this term over to the other side. So we're going to have 4x plus this quantity 2xy squared. And then we also need to divide this term here in parentheses over into the denominator. So then this becomes divided by x squared y minus 3y, like this, right? Now, we might be looking at this, you might be saying, okay, well, how do we, sure, we can isolate for the first derivative, but how do we actually get it into this form right here, which is really what it means for a differential equation to be separable. And usually, once you have something isolated like this, you want to just factor out as much as you're able to, and then see if you're able to manipulate the equation so that it gets in this form once you've done all the factoring. And we're going to go through the example right here. So in the numerator, I noticed that I could factor out a term of 2x from both terms. And if I were to take out 2x from both of the terms in the numerator, for this first term I would be left with just 2, right? Because 2x times 2 is 4x. And then for my second term, I'm going to be left with, looks like just y squared, right? Because then 2x times y squared is 2xy squared, right? I can factor out 2x from the top, and then from the bottom, it looks like I can just take out a factor of y. And that's going to leave me with just x squared minus 3. Okay. So we've done our factoring, and now what's nice is we can just move, let me say this. Now that we've done our factoring, notice that this is the numerator and the denominator both have the properties that it's some function of x, here it's 2x, here it's x squared minus 3, times some function of y, which in this case is 2 plus y squared. In this case, it's just y by itself. So we have something times x times something that only depends on x multiplied by something that only depends on y. And when you have something that only depends on x and something that only depends on y, that is kind of the clue that allows you to say, okay, this is kind of going to be a separable differential equation. So what we can do now is let's just move the y terms from here over to the left-hand side where we have our differential dy. And then we're going to multiply our dx over to the right-hand side where we're going to leave our x terms. So if we do that, I'm going to write this down in another line right here. I see that I can multiply y to the other side and divide the quantity 2 plus y squared to the other side. So that's going to leave me with y divided by 2 plus y squared times my differential dy. And then if I multiply the differential dx over to the right-hand side, I'm going to have, I'm going to have x squared minus 3 in the denominator, and then 2x in the numerator times dx. All right, and now hopefully we can see, like, all right, this quantity right here, this fraction that I have, this is my q of y, and then this fraction that I have right here is my p of x function. So now it looks like this general definition. Okay. So hopefully that makes sense. That's how we can take this ugly looking differential equation, and those are kind of the general steps to take a differential equation and manipulate it so that it gets into this form right here. And now we just want to perform this separation of variables technique where we integrate both sides of the equation and then ultimately solve for y of x, right? And this at this point it's just calculus and algebra, but maybe it's still worth going through. So I'm going to integrate both sides of this. And in order to integrate really both sides of this, you can perform a u substitution or just a substitution, a change of variables. Maybe I'll start with the left integral over here. If I'm going to perform a u substitution. So I can set u to be the denominator right here. So I'm going to set u to be 2 plus y squared. And then that means the differential du is just going to be 2y dy, right? 2y dy, like this. So that takes care of the denominator, and then in the numerator we have y times dy. So I can obtain y times dy by just dividing 2 over to the other side, right? So if 2y dy is just du, then half of that, or just y dy, is 1/2 du. It's the u substitution. Then over here, maybe I'll perform a u prime substitution. I don't know, just to give me a different variable. So over here, u prime is just going to be same idea, right? X squared minus 3. It's going to be the denominator. So then the differential of that, du prime, is going to be 2x dx. And conveniently, that's what my numerator is right here, 2x times dx, right? So there's not a whole lot to do at that point. So now what I'll do is maybe I'll come over here and just rewrite this equation in terms of u and u prime. So for my left-hand side, I'm going to have the integral of y dy which is going to be 1/2 du. And then I'm going to have what looks like 1/u, right? So this is going to be, let me just rewrite this real quick. This is going to be 1/2u, or in other words, 1/2 times 1/u du, right? Just taking these variables, substituting it back into the left-hand integral, and then for this integral right here, I'm going to have 1/u prime, and then the entire numerator here is just du prime, right? So I'm just going to have 1/u prime du prime. So now that we perform substitution, now this is pretty straightforward to integrate. I'm going to have, on the left-hand side, I'm going to have 1/2 times the natural log of the absolute value of u. And then on the right-hand side, I'm going to have just the natural log of the absolute value of u prime, like this. Okay. And because these are both indefinite integrals, there would be some integration constant coming out on the left-hand side, some different integration constant coming out on the right-hand side. I can absorb those together, however, into just a single integration constant, which I'm going to call plus c. So then at this point, I can, I guess, multiply 2 over to the other side. I want to isolate u because u is the variable that contains y, and what we're really looking for is y, right? So if I do that, let me just do this here. So I'm going to have just natural log of u equals 2 times the natural log of u prime. And then rather than doing plus c or plus 2 times c, I'm just going to absorb the 2 into that constant. So now that constant has the factor of 2 in it. Then at this point, it's really just algebra, right? So I'm going to replace u with its definition in terms of y. So I'll start with that. So rather than natural log of u, I'm going to have the natural log of 2 plus y squared equals, and then hopefully we're familiar with properties of natural logs. Instead of writing 2 times the natural log of u prime, this is the same thing as the natural log of u prime squared. But then what is u prime? U prime is this quantity here, x squared minus 3. So I'm just going to write this as the natural log of, let's see, x squared minus 3 quantity squared, and then still our same plus c at the end. And then at this point, it's just doing algebra, right? So I'll write out one more step, kind of like what Dexter does, but hopefully you can be able to solve for y of x from here. So you could take the exponential, or you can exponentiate both sides. So take e raised to that, and then e raised to this entire thing right here. When you take the left e raised to the left-hand side, the exponential and the natural log cancel out, and you're left with 2 plus y squared. And then on the right-hand side, you have e to the natural log of this thing, which is really just this thing, times e, I don't know where I'm standing, times e raised to a constant c, which you can just absorb again into some constant c times this term right here, x squared minus 3 quantity squared. And even though this doesn't isolate for y of x, hopefully it's just algebra for isolating from y of x at that point. Okay, so that would be the process for 1, taking a differential equation and writing it in this separable form, and then 2, just I guess kind of a calculus for me, right? Learn just integrating whatever function you have. In this case, they're both solved by just performing a u substitution. Okay. So that is the first technique that we're going to be looking at. We're going to be looking at these separable nonlinear differential equations. What I'm going to do now is I'm going to write out the second nice type of differential equation that is nonlinear, and we're going to spend some time showing how to solve those types next. Okay, so now we're going to take a look at this second type of nonlinear differential equation, which is kind of convenient for solving, which is called an exact equation. So let's go through it together. So we're going to start with the general form that we have here for a nonlinear differential equation. So some function q times the first derivative plus some function p is equal to 0. And this differential equation is considered an exact equation if and only if the differential form, which is this quantity, q times dy plus p times dx, is itself exact. All right. Now, this might be a bit of a confusing definition at first, so I want to really take some time to unpack this. First thing is that we have this term here called a differential form. And we can go from the differential equation, which is this, to the corresponding differential form by just looking at the left-hand side of the equation and multiplying both of these two terms by dx, right? And hopefully we see that. If we multiply this first term by dx, then we get q times dy. And then obviously if we take p times dx, that's what this term is right here. So that's the process of going from the differential equation to the differential form. And I should mention too that differential forms are a type of mathematical object. And you could make an entire video series on differential forms, and they show up in differential geometry and stuff like that. But for the purpose of this video series, we're just going to think of a differential form as, or I should say, when we hear the phrase differential form, we can just think of them as a sum of these differentials right here, or just some type of differential, d times some quantity, okay? So this is what a differential form is, and it turns out that the differential equation is exact if the differential form is exact. But then the next natural question, of course, is, well, what does it mean for the differential form to be exact, right? So let's go through that and explain what that means. So a differential form is going to be exact if, I'm going to write this out here, if there exists some function, and I'm just going to call this function f, which depends on x and y. So this thing is going to be exact if there's some function f of x, y, such that the differential form of f, or in other words, d of f, is going to be equal to this specific differential form right here. So it's going to equal q of xy dy plus p of xy dx. So if we're able to find a function f such that this differential, or this equation relating differentials is satisfied, then the differential form is exact, and hence the differential equation is exact. All right. Now, this still is probably leaving us with a lot of like, well, okay, but what does this actually mean for solving this type of equation? How do we get to the y of x equals something? So let's go about explaining that now, or try to go through the process of explaining how this connects to solving the solution. And in order to do this, if we're looking for the solution of a non-linear differential equation, and if we want to see if it's exact, there's a pretty quick test that we can perform. So we'll first describe that test, and then we can start to really connect the dots. So right now, if the differential form is exact, then this equation is true. I also know that because f is a function of x and y, by multivariate chain rule, or chain rule, whatever you want to call it, that the equation that I'm about to write is always true. I know that if I were to take the differential of a function f of xy, that needs to be equal to partial f partial x dx plus partial f partial y dy, like this, right? And this is always going to be true. This is true if the differential form is exact. So we have two different expressions for df. What we can do is now just equate the two, right? by pairing up the dx terms together and also pairing up the dy terms together. If we match up the dx terms together, then I'm going to have partial f partial x equals p of xy. Okay. And then by equating the dy terms, I'm going to have partial f partial y equals the q function, q of xy, like this. All right. So we see that if the differential form is exact, it leads to these equations right here. And then what we could do is we could then take one more derivative on both sides of these equations and then kind of combine the system of equations into one. So if I differentiate both sides of this equation with respect to y, then I'm going to get partial squared f partial y partial x equals partial p partial y. All right, it's just the act of differentiating both sides by y. And then on this right equation, if I differentiate both sides with respect to x, here's what I'm going to get. I'm going to get partial squared f partial x partial y equals partial q partial x, like this. And then because mixed partial derivatives, mixed second order partial derivatives are equal, or in other words, we know that partial squared f partial y partial x is going to be equal to partial squared f partial x partial y. That then says, okay, well, this needs to equal to this, right? So then this implies that partial p partial y equals partial q partial x. All right. Now, again, we might be saying, I can follow the literal mathematical steps, but what is this telling me, right? Well, this equation that we've just reached right here, this is an immediate condition that can be used to determine whether or not a differential equation is exact. Because hopefully we're able to follow the steps. And maybe let's just go through the steps one by one to make sure that we're on the same page. So we start with the differential equation. The equation is exact if the differential is exact. The differential is exact if the differential form is equal to the differential of some function f of xy. Now, this equation right here, in like congruence with chain rule, led us to this system of equations. Partial f partial x equals p and partial f partial y equals q. Then the system of equations got condensed down to a single equation right here. Right, so hopefully we see that if we start with the differential form being exact, we get to this equation. And this is a very straightforward check to see if your differential equation is exact, because we're going to know immediately just from whatever example differential equation we have, we're going to know what our function q is and we're going to know what our function p is. They're very easy to find. So it's just a matter of taking partial derivatives and seeing if they're equal to each other. Okay. So that's what we've done so far. Now, I want to mention this because Dexter mentions this, that the logic that we've just gone through goes from top to bottom, but you could ask yourself, does the corresponding logic from bottom to top of the whiteboard also hold true? In other words, if this condition is satisfied, or really if we have this system of equations, does that then imply that this differential form is exact? And the answer to that is, well, sometimes, but not always, not in the general case. It turns out that in order for the logic to go from bottom to top, you also require this additional condition that the domain of the problem that you're working in is what is called a simply connected domain. As if this was not confusing enough, right? And Dexter spends a little bit of time going into what simply connected domains are, and simply connected domains are definitely important to understand in the broad scope of math. But I personally think that for what we're trying to do here, just going into what simply connected domains are and why that allows the logic to be reversed, I think you start to get a little bit lost in the details and you start to lose sight of the big picture of things. So rather than going into details about what simply connected domains are and why they're useful in allowing the logic to go both from top to bottom and from bottom to top, I'm just going to mention it and say that's a fun fact, by the way, and then we're going to leave it at that, at least for this video series. Okay. So, anyways, this is some condition that we can use to determine if a differential equation is exact. Now, that's the first step needed to connect the dots here, but how do we use all of this to actually solve the differential equation? That's what we're really interested in, right? And hang with me for a second, because this is the part where we really connect everything together. Hopefully it makes sense that if we were to take our starting differential equation and multiply both sides of the equation by dx, then what we would get is that this differential form is equal to 0. And maybe let's just explain why. For the left-hand side, this is our starting equation, right? For the left-hand side, if we multiply it by dx, we said that we get the differential form. For the right-hand side, if we multiply it by dx, we get 0 times dx, or just 0. So basically, even though we haven't explicitly stated it yet, this equation right here, df equals q times dy plus p times dx, if this is our starting point, then this needs to equal 0. Okay? Hopefully that makes sense. And if the differential is equal to 0, then we can ask ourselves, well, what function, or if we take the differential of something and it gives us 0, what does that tell us about the function f by itself? Well, the only way you can take the differential of something and get 0 is if the function f by itself is itself a constant. Okay? So the general strategy behind solving exact differential equations is, well, first check to see that it's exact, right? To see that you can even apply what we're about to mention. And then if this condition is satisfied, you say, okay, the differential equation is exact. Now what I want to do is I want to solve for what my function f is. And you can ask yourself, well, how do you go about solving for what f is? Well, we have two equations, this first one and then the second one right here, that can be integrated. Integrate this with respect to x, integrate this with respect to y. That allows you to determine what f is. And then once you know what f is, then you say that f is equal to some constant. Because from this logic right here. So the idea is, once you find out what f of x is by itself, you can set it equal to a constant. And now you have some expression on the left-hand side that has various x's and y's in it, because this is a function that depends on x and y, and it equals a constant. So you can just algebraically isolate for y, and then that is how you obtain your solution. Because after all, the solution to this differential equation is just y of x equals something. And now this is the means to go about doing that. Okay? So there's a lot of stuff kind of going on in here. And I really think that this is best understood. We might be able to say, okay, I sort of get what's going on, but I think we'll really solidify the concepts with an example. So I'm going to erase the board here, and maybe, we'll just write the example. I'll leave the definition up for an exact equation, and then maybe I'll leave this, I'll put this up here too, because this kind of is like the final implication for what this is a starting point, this is the ending point, right? I'll leave this up here, and then we'll go through an example to finish off the video. All right, so we have this example differential equation that will hopefully kind of make sense to be like, okay, this is how we solve nonlinear differential equations of this form right here. First thing that I'd actually recommend doing, and I'm not going to do this here, but I'd recommend doing this on your own, is to check if this differential equation is separable, right? Because if it's separable, we already have this technique for solving that. And usually separable differential equations are more straightforward to solve than exact differential equations. So I'd recommend, try to separate this and see if you're able to or not. Turns out you can't, or at least not. If you go through the steps that we went through in the last example, you'll run into problems. But try it yourself and convince yourself that it's not separable. But we still have this differential equation that we want to solve, and we want to first check that it is exact. The condition that we use to check that the differential equation is exact is this equation right here. So partial p partial y is partial q partial x. So let's just identify what p and q are in this equation. And that's what's nice about differential equations of this form, is we immediately are going to know from the very beginning what p and q are. So q is all the stuff attached to the first derivative. So that's going to be this part right here. So this is our q. And then this part right here is going to be our p. Say, okay. Now we just need to see if this equation is true to determine whether or not this specific differential equation is exact. So let's first take partial p partial y. So partial p partial y is just the derivative with respect to y of this quantity right here. So it's going to be 2x minus 3y squared. And if we differentiate this, that's going to go to 0, and the second part is going to equal negative 6y after we differentiate. Say, okay, partial p partial y is minus 6y. Now let's just compute partial q partial x, which is just the x derivative of this term right here, which is, all right, rather than as 6y times y minus x, I'll just write as 6y squared minus 6xy, like this. And then when we write it out this way, this term goes to 0 because there's no x in here, and then this term is like constant times x, or in other words, just minus 6y. So this is cool. We've taken the partial derivatives of both of these terms, and we found that they're equal to each other, which tells us that this condition is satisfied, meaning that the example differential equation that we have right here is an exact differential equation. Okay, so that would be the first step, right? Showing that the differential equation is exact. Oops. Now that we've shown that the differential equation, is exact, now we want to actually solve it, right? And that's going to involve finding that f function, right? If we remember from the previous whiteboard, I probably should have written it out, but I'll just remind us right here. We were led to the system of equations that partial f partial x is equal to p, and partial f partial y is equal to q, right? That was the system of equations that we were led to in the previous whiteboard. So what we want to do is we want to use the system of equations to solve for our function f. And finding f is really kind of the whole process for solving or obtaining the solution to this differential equation. And I think we'll see what I mean here in a second. So let's start. We have two equations to work with, and we need to find f. So let's start with this first equation right here. And maybe if it's okay with you, I want to erase these two lines, because these two lines are just confirming that our example equation is exact. We've already done that. So once we don't need to do any more with these two lines once we've established that. Now we want to work with these equations right here. So I'm going to start with this equation, partial f partial x equals p. So partial f partial x equals this right here, so 2x minus 3y squared. And if I want to obtain the function f by itself from its partial derivative, I just need to take both sides of the equation and integrate them with respect to x. So let's do that. So if I integrate this left-hand side, if I integrate the left-hand side with respect to x, and if I integrate the right-hand side with respect to x, let's see what I get. For the left-hand side, I'm going to get just my function, f of xy by itself. And then for the right-hand side, let's see what we get. We're going to get If we integrate the first term, we're going to get x squared. If we integrate the second term, we're going to get, with respect to x, of course, we're going to get minus 3x y squared. And then because this is a indefinite integral, I'm going to have some integration constant, which I could call g. Now, the reason why I'm calling it g is because this doesn't, in the general case, this doesn't need to just be a constant, but this could be some function of y. The reason being because we're differentiating, or we're integrating here with respect to x. You can imagine if I were to take my function f and it looked like this, I were to take the derivative of f with respect to x, in other words, I were to compute partial f partial x, then I would be left with 2x minus 3y squared, and then differentiating this with respect to x would go to 0. So this is the most general way that we can write an integration constant because f is multivariate, okay? So hopefully that makes sense, that this is just the form that I'm going to take for the integration constant. And this is all for the first equation right here. Now let's go on to the second equation. Partial f partial y equals q. I'll do that over here. So partial f partial y, if that's equal to q, q is going to be this term right here. So this is going to equal 6y squared minus 6xy. And same idea, if I want to obtain f by itself, I just need to integrate this with respect to y, or integrate both sides of the equation, I should say, with respect to y. And when I do that, let's see what I get. For the left-hand side, we're going to get just the function by itself. Then for the right-hand side, if we integrate this term, this is going to be y squared goes to y cubed, and then we divide by 3. So that's going to give us 2y cubed for the first term. Integrating this with respect to y is going to give us y squared divided by 2, so minus 3xy squared. And then because there's going to be an integration constant, because it's an indefinite integral, in the general case, I can write this as some function that only depends on x. Hopefully we see how we did that there. So we have two different expressions for f of x, y. This is one of them, and this is one of them. But now we just need to find out what these integration constants are, g of y and h of x. All right? And what we can do is we can say, all right, whatever our function is, it's going to be x squared minus 3xy squared plus something that only depends on y. So let's look at this form of f and see if there's a term that only depends on y. If we do that, we see, oh, it looks like that term right there only depends on y. So this mystery function, this g of y integration constant, we can say, because we have this clue also, we know that g of y needs to equal 2y cubed right here. So okay, that's the first part. Then let's find h, and this is a little bit redundant, but it's always a good check to find both g and h. We know that f of xy should be 2y cubed minus 3xy squared plus something that only depends on x. So let's now look at this form of f and see if there's a term that only depends on x. And by doing that, we see that this first term here is x squared. That only depends on x. So it seems like h of x here should equal x squared. Okay. So hopefully we see how we can piece together those integration constants from using both of those equations simultaneously. And now, after doing that, we should get the same thing for this version and this version. After all, they are the same function. It's still the f of xy function. So let's just write this out one more time. F of xy should equal x squared minus 3xy squared plus 2y cubed. And that should match both this and this right here, and it does. Okay. So hopefully we understand that process, the act of obtaining this function f of xy. Now, the fact that this differential equation is exact, we said that basically df goes to 0. In other words, this equation right here is equal to a constant. In other words, f of xy is just equal to some constant c, like this. What that whatever this constant c is, this would be specified by the initial conditions in the problem. So if we were provided this specific differential equation, and we were also provided that y evaluated at x equals 0 is some y naught, then we could solve for what c is. But at this point, we're done, assuming that you solve for c, right? Let's see. We can actually solve for c. Let's say we're provided this and we want to solve for c. What we could do is we could take this equation, x squared minus 3xy squared plus 2y cubed is equal to c. That should be true for all values of x and y. So if I plug in x equals 0, y equals y naught, I get 0 squared minus 0 plus 2y naught cubed equals c. So if this is the initial condition provided, then it turns out that this constant right here is going to just be 2 y naught cubed. And now we would be done with the problem. Now you might be saying, well, this isn't in the form y of x equals something, right? And what I would say to that is, well yeah, but there's kind of like this step where it says, in theory, you would be able to algebraically solve for y. You could go through algebra and ultimately solve for what y is in terms of x. Doing that, you can see, would require a lot of algebra. In some cases, it's not necessarily possible. The cases where it's not possible to just get y equals something are the cases where nonlinear differential equations simply don't have that analytic closed form, nice looking solution. But what you can do is you can say that this equation right here, this is an equation that if you were to plug this back in to here, you would get that the equation was valid if you were able to somehow solve for y. So usually what happens is people leave the equation at this point and say this is the solution, even though it's not in the explicit form y of x equals something. Okay. Hopefully that makes sense in connecting the dots, seeing how first we could start with an equation, a differential equation, how we can check that it's exact, and then how once we know it's exact, we can solve for that f function and then, I guess, obtain the solution from there. Okay. So that's all for this video. In the next video, we're going to kind of take a closer look at these types of solutions, because this, again, this is the first type of differential equation solution that's not in the y of x equals a blank form, and show how we can still try to understand solutions to these nonlinear differential equations, even if it doesn't have that nice looking form. Because what we'll see is that there are a lot of systems, just physical systems in various areas of study that involve looking at nonlinear differential equations, where even if we don't have a form that we can just write out on a board, we might still be interested in what the solution looks like. So we're going to take a look at that in the next video. But yeah, that's all I have for this one. So thanks so much for watching, and hopefully see you in the next one.